So we have another BmMT problem. So this was number 18 on the team test. So we have two people are playing game, and the kid repeatedly writes the digit 2023 in this order from left to right until Richard tells him to stop. So Richard wins the game if the resulting number as a base 10 integer is divisible by as many positive integers less than or equal to 12 as possible. So this is the key point, I guess. So we wanna find as many divisors as possible. I mean, as out of the first 12 integers, and when we stop. So which means if we can get a number that is actually divisible by all 12 of like first integer, then that's the number we are looking for. But if not possible, then we need to get as many of those 12 numbers to be divisor of our number when we stop. Okay, so for example, like we are told like when Richard stops Ankit after 7 digits. So this is the number that we have 2023, 20, and 2. So these are the 7 digits. And then when you check the divisibility for each number, so 1 and 2 is the only divisor of these numbers. And then we want to make sure that's going to happen as early as possible. Okay, so let's see how we can do that. First, let's kind of see small cases. Like we can have like only 1 digit, let's say 2, or we can have 2 0, like 2 digit, or 2 0 3 or 2 0 2, or we can have 2 0 2 3. So we can just say these are some of the early observation we can have. So and then you can go back to 2, or you can have 20 23, and then you got to 0, and you can keep trying listing more, right? But our goal is just to see 1 2 3 4 5, all the way to the 12. So we want to get as many divisors as possible from the number that we are gonna stop, right? So the first things we probably want to know, since we are gonna repeat 2023 some number of times, and then we will get maybe some after some other integer like the digits, so all those 4. So we kind of want to probably know about the prime factorization of 2023. So 2023 is 7 times 17 squared, which is a good reminder that we kind of need to remember the prime factorization of the years anyway. So that's going to be the case. So like if you have 2023, for example, like some number of times like repeating, then you're going to get a number that is going to be multiple of 7 and 17. So which is that is 7 a divisor will be if you just end up your last digit to be 3. So if that's the case, right? So what I mean by that, like let's say we stop after 2023, let's say, right? So 2023, if you stop right here, so this number is divisible by 7. But the problem with this is also divisible by 7. If you add some number of like 2023s after that, any number that we get is going to be divisible by 7. But the problem with this, the last digit is odd numbers. So in that case, like the number is not divisible by like 2, 7, 4, 6, any even numbers, which means a lot of numbers that will not be divided. So for that reason, we don't want to choose the last digit to be 3. So which is why this variation is actually not a good one. Okay, so that is going to be a divisor of 7, but 7 will be divised, but most of the other numbers will not be. So which is why we don't want to take that one. So then the question is, which variation, which means like what last digit might be was the best option. So you can try like 20 or maybe 32, because these are the odd like even numbers, and at the same time, like this is like if you have 202, that's just 101 times 2, which is not going to be many divisors either. But 32 and 20 looks better, because when you take 20, that has like 0, which is divisible by 5, and any like maybe 2, even 4. And the same thing with this guy, but this is not divisible by 5 either. So which is but divisible by 8, but this may not be divisible by 8. It depends on the previous digit, right? So for that reason, I will say we can just kind of start with one of these two cases and see which one is going to give us the best one. Since 20 is a divisible by 5, but 32 is not, so which is I should go with 2 zeros as my last digit, because that is actually going to add 5 into our list of the divisor, but when you take the 32, so 5 is not going to be a divisor, so we want to get as many as possible. So we should go with the 20. So based on this reasoning, then our numbers should be look like this: 20, 23, and 20, 23, and some number of 23s, okay? And then at the end, so you have 20 one more time. But the number of 23 is not known yet. But at least when this is the number that we are gonna see, so that's like divisible by 1 for sure, divisible by 2. And then we are gonna try finding this number to be divisible by 9, but we can just kind of go with the 9. As long as this number is divisible by 9, that should be divisible by 3 as well. So which we will look for. And then since last two digit is 20, which is multiple of 4, so that's gonna work, and 5 also works. And if you can find a number that's multiple of 9, then that will give us multiple of 3. So since this is even, that will be also good for 6. So everything will be fine. And 320 is actually divisible by 8, so that does work. And then the last 3 is 0, so it should be fine. And when you have a number that's divisible by 4 and 3, that should be divisible by 12. So most of these are going to be good. Only 2 numbers are gonna need to be checked, right? So we cannot have 7 at all, which means at most we can get 11 if possible with 9 and 11. But 7 is not possible because when you look at any other ways, then none of them was divisible by 7. So which is why we just remove that one, because otherwise we were not gonna get a lot of even divisors. Okay. So then let's check the 9. So to get the 9 as a divisor, the sum of the digits should be multiple of 9. So first thing, we do not know how many 23s are available, but when you add the digits, so 4, 2, and 3, which is like 7, and then you have, let's say, n of these 23s, right? So that means 7 times n will be digit sum, plus at the end there will be 2 and 0, which is 2. So this has to be a multiple of 9. So I'm gonna say 0 mod 9. Okay, this is something, but for the 11, which we are going to find the number n, so let's try this congruency. For 11, when you add the digit in skipping 1 by 1, and those sum should be have a difference of 0 or 11. So, but let's think about this way. So if I take these numbers, that's 4, and then the other 2 numbers is 3. The difference between those every other numbers is 4 minus 3, which is 1, which means when you have 23 once, the difference is 1. When you have 2 times, that will be 2. If you have 3 times, that will be 3, and stuff like that. In that setting, if you have n of these 23s, that difference, the sum of the differences will be n. But at the same time, we have 2 other digits at the end, and then 2 corresponds to it will be added to the digit sum in the first sum. So 2 this 2 all the way to this one. For when you ignore the last 2 digits, the difference of the sums will be n, right? And then we have 2 extra right here, so we can just say n plus 2. So I hope that makes sense. So that should be n plus 2, 0 mod 11. Okay, so then we just want to solve this congruency. So this guy could be written like, if you subtract 2 from both sides, you get -2, and add 11, so you will get 9. Or you can just say 9 plus 2 is 11. So that's going to give us 0 as remainder. So that should be mod 11. Okay, this is something. And then in this case, you can plug numbers into this congruency until you get something that's multiple of 9, which is obvious for n is 1. So I can say n equal congruent to 1 mod 9. So we have a system to solve. So you can go ahead and plug numbers. There are a couple of ways, but I'm going to use the system as used in Chinese remainder theorem. So if I want to write this congruency as, let's say, n equals, maybe I should write general n equals 1 more than multiple of 9. So that could be written as 1 plus 9 times, let's say, a. And that is equal to 9 more than multiple of 11. So 9 plus 11b. So since we want to get one of these variable to be constant, maybe we can take the mod 11 or 9. I'll take the mod 9. I take mod 9 to remove this coefficient of a. So that will be 0. So 1 plus 0 will be just 1. And then that will be congruent to, this is going to be 0. So 11 will be 2. So 2 times b mod 9. Okay. So this is good. Now we do have 2 times something is congruent to 1 mod 9. So you can just say what number I should multiply b, 2 by, so I can get one more than multiple of 9, so which looks like b is 5. So I can say this is b is congruent to 5 because 10 will be one more than multiple of 9. So that should be mod 9. And I can just write it b as like 5 more than a multiple of 9. I'm going to call that 9k. K is some integer. So the question is what we are looking for is the n, and we know b is equal to this. So I can plug into this guy, 9 plus 11b, so 9 plus 11, and then b is this guy, so which is going to be 5 plus 9k, k is integer, and then that would be equal to 5, 11 is 55 plus 9 is 54. So we got 64, 64, right? So we have 64 for this guy plus like 55, 99k. The meaning of this, the n value is gonna be 64 plus a multiple of 99. So the least number is 64. So meaning that we can say the n is at least should be 64. And the goal was the number of digits that we are going to get at the end, right? So n was the number of 2023, so which means if you have 64 of those 23s and each 23 has 4 digits, and then at the end we have 20, which is 2 more digits. If you do 4 times 6, 24, that's 240, and then you got 4 times 4, 16, plus 2, which is 18, so 258. So we do have 258 digits when Ankit Ankit was like stopped, right? Anyway, so I hope that was clear. So the goal is just to kind of write the congruency statements and then to see how we can solve that problem after that. So I said the Chinese remainder theorem, but just we didn't really talk about the Chinese remainder theorem. We just write the congruence as an equation and then go from there. There is a way to kind of formulate the Chinese remainder theorem to find a solution, which is kind of too long. I wouldn't bother that, to be honest, but this is actually okay to do so. Anyway, so I'll see you in the next video.